Imagine a colossal sunshade, a staggering 1,000 kilometers in length, orbiting silently between Earth and the glaring sun. Its purpose? To control the amount of sunlight streaming onto our planet, perhaps to aid in combating climate change, or to create a more stable climate. However, what if a segment of this immense structure were to catastrophically break away? The consequences could be both fascinating and potentially catastrophic, opening a space for thought experiments and theoretical explorations. Picture this. The broken segment acts like a giant cosmic magnifying glass. Its geometric breakage causes sunlight to converge rather than diffuse, funneling concentrated solar energy along Earth's orbital path. To understand this better, let's use the analogy of a child's playful tool, a simple magnifying glass. This optical marvel works by bending sunlight through its curved lens, focusing it to a point where it's intense enough to ignite paper or dry leaves. Similarly, when the sunshade's fragmentary lens focuses solar radiation, it concentrates sunlight to approximately 700 watts per square meter, a significant intensity given the context. The mathematics behind this involves calculating focal lengths, which depend on the curvature of the lens, here, an unintended outcome due to the segment's fracture. The focal point is determined by both the curvature and the material properties of the segment. When sunlight hits this focal region in Earth's orbit, the previously harmless sunlight is transformed into a concentrated beam, raising pertinent questions about its impact on space objects. What emerges as a primary concern is the potential for thermal ignition in satellites, the International Space Station, and other spacecraft. Our technology-laden satellites, designed to function efficiently within specific thermal limits, could suddenly find themselves bombarded with an unexpected surge of concentrated solar energy. This influx threatens to overheat delicate instruments, risking catastrophic equipment failures or even causing fires within the satellite's own systems. The ISS, housing human life amidst the cold backdrop of space, faces a greater peril. Although shielded and equipped with thermal controls, it wasn't designed to withstand such spontaneous thermal assaults. The need for contingency plans becomes paramount to avert any potential crises in space. Now, let us turn to how we might mitigate such risks. Engineers and scientists propose implementing diffraction edges along the broken segment's circumference. These edges would work much like the diffusing patterns on a DVD, scattering light instead of concentrating it in a single direction. By deliberately introducing diffraction, the segment's potential to focus sunlight into a powerful beam is diminished, returning the radiation to a more evenly dispersed state. Furthermore, space agencies could activate an attitude-safe mode in susceptible spacecraft. This mode would reorient satellites or instruments away from incoming focused radiation, keeping them shielded from direct exposure. An ingenious solution to safeguard critical infrastructure far from home. Lastly, implementing an autonomous tumble response in affected satellites could be pivotal. Imagine satellites strategically spinning or rotating to avoid prolonged exposure to the concentrated beam, distributing thermal loads until either the threat dissipates or other mitigation measures are enacted. In conclusion, while the scenario of a sunshade fragment creating a focused beam of sunlight poses a captivating thought experiment, it also serves as a reminder of the complexities and interdependencies of our cosmic endeavors. Through understanding and orchestrating clever engineering solutions, such as diffraction edges and autonomous satellite defenses, we can aspire to turn potential threats into opportunities for advancement in our efforts to manipulate and harness the cosmos. Here lies the essence of innovation, where imagination and science join forces to redefine our relationship with the universe.